the next one, which is unpacking manually with Ollie Debug and PE Studio. So all the tools you need are already in here. So I'm going to start with Putty. And let me get my cloud machine up, which is here. All right. So I'm going to get that version of Putty. I don't care about this text document or this. I just want the instructions, which will be here. 121. All right. So I want to get that version of Putty. Putty is just a common Windows SSH client. There's nothing particularly special about it. It's just a program to work with. So I'll download this into the downloads folder. That's fine. And all right. Now it might be blocked. When you download things, Windows often decides it's not safe to run. So if you double click it, and this is okay. It asks, and I'll say yes and run it. So that's good. Sometimes you have to right click it and go in the properties to unblock it, but it's running okay. All right. And then I want to check the hash. Unfortunately, Windows doesn't have a built-in hash calc, but to be fair, they have a signature system, which is perhaps even more important, although we are going to see that it has some strange undesirable properties. But anyway, I can use hashcalc to make sure that this program is intact. And so the MD5, for example, starts with BA7, and it should start with BA7. So this file is intact. If it was modified, these hash values would change. And if you want to be fancy, the most reliable one is the SHA-256, but in practice, the MD5 and the SHA-1 are very strong evidence that it hasn't been altered. So if you run Putty to just see what it does, I should have the folder open here, my downloads folder. If you run it, it lets you connect to an SSH server. I've got one at ad.samsclass.info. And of course, they're all over the place. And when you connect, it asks you something about a host key. Just say yes. And then it asks you to log in. And it prints this message, login as. And this is all I care about, is this much functionality. We are going to modify this program to print a different message here. That's all. Just to learn how programs run and how to modify them. And this is how most people begin learning reverse engineering, is they learn how to cheat at games. Windows games. But first we're going to look at what compressing does. So we're going to make a compressed version of Putty. So I open a command prompt. All right. And I put my file on the downloads folder, so that's where I'll go. And now if I do a directory, there's a bunch of stuff in here, but one of the things that's in here is Putty. So that's fine. And I can compress it with UPX. UPX-O, Putty compressed. Putty. I can probably copy and paste this since I'm just going into the same machine. Let's maximize this window. There we are. Now right click should paste. Oh, all right. Copy and paste appears to have failed on me, which tends to happen. Right click, copy. Right click should paste. Okay, this time it worked. So this is going to do UPX. The default action is to compress a file and puts the output in Putty comp. So that should do it. And there you are. It shows how it works. It was 531K. It zips it down to 267K. So now I have Putty comp. All right. Going back to the instructions. Now we're going to check the hash again. The hash should now be C66. So let's do that. I don't know if I still have hash calc running. I don't, so I better run it. All right. And I should be able to just drag and drop that compressed file into hashcalc. Yep, and I have C66, so that's fine. It had the desired effect to compress it. All right, now we can launch it and then look at it in PE Studio, which is good, clean fun. So if you run the compressed version, even though it's half the size, it runs exactly the same. Because what I was saying last time, when it unpacks into RAM, it creates the same RAM image as the original file. So you can do the same thing, go to a server here like ad.samsclass.info and open, and it will I put a comma instead of a space. That's the problem. A comma instead of a period. ad.samsclass.info. There. Open. And it does the same thing, prints the login as message. So the compressed file functions. It's just smaller. All right, so now we can use PE Studio, which is a very nice utility, to see a lot about a file. And so I can open Putty, the original Putty, from the Downloads folder where I put it. All right, and now this tells you a lot about the file. It shows you the hash values, and it shows you the entry point. In the first few bytes of assembled code, it tells you what it was compiled with, Visual C++ version 7. It sends it to VirusTotal and tells you what VirusTotal tells you, and there is one engine called Apex, which is foolish enough to mark this Putty as malicious, which is pretty ridiculous. But virus engines tend to have a lot of false positives. As I mentioned before, a couple weeks ago, a bunch of them started blocking my website, which happens every year or two. They seem to just have, like, amateurs look at things and decide if they're malicious, some of these engines, and rumors pass, causing them to... It's quite common that some of the engines will mark a harmless file as malicious. All right, and let me check what other features I want to point out here. Okay. Indicators and VirusTotal, yeah, we've seen that. And the sections, all right. So if I go here, all right, here's the sections. Here's the normal sections you'll see are text section, our data, data, and resource, all starting with a dot. The text section contains assembly language instructions, really machine language instructions, which are pretty much random bytes. The entropy is a measure of randomness, a quite handy trick to get a general idea of what's stored somewhere. And this is entropy 6.6. The maximum possible is 8. So if you have compressed or encrypted data, it will be nearly 8. 6.6 is very random. That's assembly language, machine language. Here's 6.0 for this R data stuff, so that's probably something like images that are compressed. Here's 2, a low entropy for the data. That's probably something like strings, which are not really very random at all. They use only printable characters, and they appear in patterns like spelling out English words. And the resource section is kind of in between. So that shows you, those are the 4 sections of this file, and they will load into memory. And here you see the libraries used, which we've already seen before. For other programs, Advanced Windows API, and this one is going to have to make an internet connection. And I'm not seeing the internet connection library here. I expected to see like IE. Yeah, you must be using low-level network sockets. That might be why that one engine is freaking out. Anyway, there's the imports. These are the actual functions it uses. And there aren't very many of them. Here's get open file. Anyway, so there's general information about the file. And we can check the entry point and the permissions. Let's go back to the sections. Here are, should be able to see permissions. Why am I not seeing the permissions? Let me go back to my instructions. Here. Oh, file type executable. Yeah, but where are the permissions section by section? Click sections. I should see permissions. Text is, oh, I see. There. Yes, executable X, writable X. Okay. This is important. Only this section is executable, and it is not writable. This is a fundamental security principle of Windows and all other modern operating systems. You're not allowed to have a memory region that is writable and executable, because that's how code injection attacks work and most memory corruption attacks. You write to something like a password or something like that, and then you write code which you then execute. So to prevent that, you're not allowed to have writable and executable permissions on the same memory segment at the same time. Windows does not enforce this, however. You can write a program that breaks this rule, but this program, Putty, does not break that rule. One fun fact is the Raspberry Pi version 3, everything is both writable and executable, which is a serious security weakness of that device. But anyway, that's a little bit of information to see about the original Putty. And the entry point is also worth noticing. The entry point here is 550F0, and that is in the text section. You can see the text section starts at 5C1000 and goes on from there. And it is 401,000 and size 5C1000. So anyway, it turns out this address is in that section, which is what it should be. All the executable code should be in the text section, and you should enter by entering the text section. That's the normal program. And so let's take a look at the compressed program, which is of course going to be pretty different. So another instance of PE Studio. Here we go. We open the compressed version. Putty comp. All right. And so if we look at the sections, which are here, still loading. Well, let's look at virus total. That's ready. You know, the other one was only detected by one engine. This is now detected by 9 engines. Just the fact that it's compressed is triggering them. And this is, again, a false positive, but it's not totally unreasonable to say that things probably shouldn't be packed with UPX. That's suspicious. That's not normal. All right. And wait for the sections to cough up their answer. There we are. Now the sections have these weird names, UPX0, UPX1, and .resource. This one's normal. That's actually a bug in the UPX packer. The author of this open source packer misspelled the resource section, so it actually doesn't get compressed. Intended to compress it, but it doesn't happen. So this section is rise0. It's just an empty container. And the UPX1 is where all the data is. And look at this entropy 7.9. That's compressed data. All the wasted space has been squeezed out. The information is packed into the minimum size. And that's all the compressed data is there. So that's the story here. Notice everything is writable and executable, both of these sections. Another sign, and it's highlighted in red because PE Studio has detected that as a sign of malware. That's not right. Another thing that's not right is the entry point, which is a strange number that does not point into a text section because there is no text section. So there's quite a lot of red flags here for this thing showing that something is not right about this program. All right. Anyway, so that's the one way to look at the overall feature, all right, of these programs. And we can check the imports. And I think the only important difference is in Putty comp, you'll see less imports. So here's the Putty, the real Putty, and the imports are here. And you see they go all the down the page. And if you look at the other one, imports are here. It's having trouble finding them. But if it did find them, you'd see there weren't as many. All right. Anyway. So now we already have, you hopefully already have your samples. There's a sample here to just put in PE Studio to get a flag. And then there's Ollie Debug, which is already installed here. So we're going to look at these with Ollie Debug. Ollie Debug is your best friend. This is how most reverse engineers get started, is using Ollie Debug to cheat at Windows games. So Ollie is a debugger, which is a lot of fun. You can analyze Windows executables and mess with them. So here's Ollie Debug. I'll just say yes to these library questions. I don't have administrative rights, which is fine. I'm just trying to analyze userland code. So if I open Putty, which is in my downloads folder, there it is. All right, so Putty loads, and let me make the font bigger. Options, appearance, fonts, change, and make it bigger. There. All right. So what you see, this is a real important thing to get used to. Ollie Debug is the original debugger. Everyone got used to using it. A whole bunch of later debuggers that all imitate Ollie Debug. The layout is always the same. Here you see the machine language instructions that are going to run the program. And they're turned into readable assembly language here to make it easier for a human to understand. So you see things like push and call and move. Down here at the bottom right, it tells you the program is paused. That's where you should always start when you're using a debugger. When you load a program, it loads it into memory and then stops because it assumes you want to examine or alter the action of the program, so it's not running right now. You can run it with this run button, but it starts in a pause state so you can examine it. Here are the registers. The registers here are little memory locations inside the processor. EAX, EBX, ECX, and EDX are general purpose. The stack is little temporary regions of memory where you store addresses to return from modules, and at the top of the stack is the ESP, and the bottom is the EBP for extended base pointer. And here's the EIP, set aside because it's really important. That is the one that controls which instruction will be executed next. So an attacker who wants to exploit a memory corruption vulnerability is typically trying to gain control of the EIP. If you can redirect execution to move to a different location, then you can take over the box. So that's what these are. Down here is the stack itself, just shown. So if I resize this to make it readable, come on, there we go. That's the address, and here's the value. Notice the address just counts up 4 bytes at a time because this is 32-bit code. So each 32-bit word contains an address, and the ESP is from FF74 to FF80, and that's what you see here, FF74, here's FF80. So these 3 bytes are the current stack frame, and as you see, they include return addresses. What happened is we launched this program from Windows. Windows moved into the program and then stopped, and these are the return addresses that will be used to go back to Windows if we exit the program. That's what you see here. These are your breadcrumbs to go back to above where you are. And over here is just an area to dump any area of memory you want to look at in a hex dump. So you have addresses, it starts with some default value, and you can examine any part of memory you want to here with just hex and ASCII. So that's the basic layout. And this particular so this is the real program Putty that's going to do this. And if you run it inside the debugger, it will run. It's a little bit slow, but it does run and pops up the window here. And you can continue to use it, like put in ad.samsclass.info, and it will run and pop up the box and say login as. All right, but I don't really want to keep running it, so I'm going to get back to the initial state with debug restart, something I do often in debuggers. If you end up somewhere you don't want to be, debug restart puts you back in the original location. Now let's look at the compressed program in OllyDebug. I just want another copy of OllyDebug running, and I'm not an administrator, but that's fine. I open PuttyComp. Now, OllyDebug notices that PuttyComp is messed up. It says this code section is either compressed, encrypted, or contains a large amount of data. Do you want to continue analysis? I'll say no. It has noticed that this is not a normal program because it's compressed. So I'll make it big, and I guess I have to change the options again. Change to make the font bigger. All right. Now, just resize this so we can see it. Notice something already is strange. If you look at these instructions, it's push add, move, load address, push, and there's nothing over here, which means it did not recognize any normal Windows calls. But if you look at the real Putty, it's different. It's push, push, call, and right here it's calling a Windows API get version EX. So the compressed program is not running the normal Putty code. In fact, this normal Putty code, push 60 and so on, is not going to be found anywhere in here. Instead, it does push add, which is different. This is the decompressor. It's not Putty. And it's so small, you can just page through it with the scroll down key. In fact, page down, it'll be just a few pages down. This is the decompressor. And when you hit the end of the decompressor, it'll just have a bunch of zeros, which it is confused about. So this is the decompressor to go down to this point. And this jump is to initialize, is to jump into where the decompressed Putty is. So I can put a breakpoint here with right-click, breakpoint toggle, or by pressing the F2 key, The red there tells you it'll stop at this point. So now, if I look at the memory with View Memory, I can see the memory sections here. And so here's the PuttyCom sections, UPX0, UPX1, and resource. And I can dump this, right-click, dump, and see what's in there. And UPX0 is just all full of zeros. There's nothing in there right now. It's just an empty container to be filled with code. UPX1, if I dump that, this is full of random data, which is being misunderstood by the debugger as assembly code. This is just random data right now. This is compressed data. All right. Now, so what I'm going to do is run the program up to this point by going back to the CPU window. And now, when I run it, it's going to run to the breakpoint at PuttyCom. It's down to this point. It's about to jump into there. So then I'm going to press F7 to make one more step, one more instruction. And now I'm here, and notice this is the stuff that we saw before. Push 60, push PuttyCom, kernel get version here. This is the real genuine Putty code. Just what you see here. Push, push, call, move, get version. This is the unpacked code. And you can see the unpacker here with View Memory. Now, this section that was all full of zeros, if you right-click and dump, is now all full of instructions. This is the right machine language instruction. Now, in the project, I used an old-fashioned way to extract this. There's an Ollie extension just for this purpose that will extract. This is called manual unpacking. If somebody has packed their code and they haven't used an open source packer like UPX, and you can't figure out what the unpacker is, you can just use the malware itself to unpack the code. Find the part of the malware that unpacks it, run the stub, and just dump it from Ollie. And there's an extension which I used here called Ollie dump, and you can use that, but I found out I don't really care about that so much, and I've gotten away from using Ollie dump because it isn't an equivalent unpacker extension for later debuggers like Immunity, and you don't really need it. All I want to do is find the strings. And you can just dump the memory section right inside the debugger. So if you go here, here's the unpacked code. I can just save this with right-click, backup, save data to file. And it's going to put it in documents. I think I'll put it in downloads just to be consistent. And this is PuttyCom memory. That's perfectly fine. I can save that. And now, if I look at that, I'm going to find the strings, which is really all you're going to get with this method anyway. So I can use bin text, which I think I have on my desktop, yeah. And I can view the strings in that decompressed file, which I put in the downloads folder. And there it is, the decompressed memory. And let's make this big. And use page up. I saw something up. There we are. Looks like junk. Oh, this is the code section. I thought I was going to find good strings in here. And there I find like an alphabet. I'll go back to my project then. See, let's go back to here. All right, so anyway, you can also dump it with this extension where you give it the starting address and then examine the dumped file in PE Studio. That's another way to do it. One thing I've found is these manually unpacked things don't really run. It's not perfect. And the main thing I find is you can usually see the strings, although I didn't get the strings this time. Anyway, that's manual unpacking. It's a very powerful technique. I've used this for PHP malware and lots of things. It works for encryption and decompression. It's often much easier, rather than really figuring out exactly how malware encryption and compression work, to just find their code that decompresses it. It has to be in there. Just use their code. Of course, as I mentioned, the problem is you are running malware. You're running part of the code in the malware, so you always have to be working in a disposable environment, because you'll often accidentally run some of the malicious part of the malware along with it. Yeah, like a malicious machine learning. All right. So let me stop this one.